search the recesses of space. There in the darkness, they found something huge, dense, and invisible. Slinging stars at a whopping 240,000 kilometers per second, or 8% of the speed of light. They were unable to capture any image of the mass. Left to observe the effects it was having on its surroundings, scientists could only make guesses at the cause. While we have long theorized that it could be a black hole, we can now put our suspicions to rest. We have obtained photographic proof of what is at the center of our galaxy. Welcome to Factnominal, and watch as this black pearl is unveiled to the world for the first time. The Event Horizon Telescope (EHT) captured the first image of this supermassive black hole at the center of the Milky Way. Found in 1974 and named Sagittarius A star. It is only the second ever black hole to be photographed. The unique device that did this has also been used to photograph the distant Messier 87 galaxy's own black hole, M87, in 2019. In order to capture our Goliath in action, the scientific community combined the efforts of more than 300 researchers from 80 different institutes. They have worked together to create the Event Horizon Telescope (EHT) collaboration. In an amazing alliance, 8 pre-existing radio observatories around the world worked collaboratively to gaze at a precisely calculated location. Each organization collected data separately and sent it physically from person to person to be analyzed. Linked together across the globe, this daisy chain of radio dishes collectively creates an Earth-sized telescope. John Carlstrom, the professor of astronomy and astrophysics at the University of Chicago, explains that.
We want to build a telescope the size of the Earth, but we don't have to actually cover all the Earth. We just need to have pieces of the telescope that spread out over the size of the Earth.
This revolutionary system of linked devices has created an entirely new apparatus. The Event Horizon Telescope offers some of the highest possible resolutions available from the Earth's surface, thus bringing extreme detail and visibility to previously concealed parts of our galaxy. All of this work was being done to photograph the invisible anomaly sitting roughly 25,000 light-years away. Our little pearl was just waiting for its moment to shine, but it wasn't an easy task. It was the equivalent of attempting to take a picture of a donut on the moon, as we had to filter through billions of stars to get to it. This vast network of people, equipment, and organizations are all working together to bring these data-drawn images to the public. There are several subdivisions of the EHT, all of which have different assignments. Image interpretation and connecting different arrays together to work as a single eye are just a few of them. Every observatory has its own tasks to complete in order to contribute to the greater project. There are even branches that are producing simulations of black holes to compare with real-time observations. Alongside their separate duties, each telescope has an observation period. For multiple nights in a row, they gaze for hours at Sag A star. This is the same technique used by photographers to take bright pictures of the night sky. Scientists are essentially utilizing the long exposure setting on their cameras. The lens is exposed to the light of stars, and the longer it's exposed, the more light it absorbs. Because of this process, the picture that is produced is much brighter. Another analogy used to explain the imaging process is one of taking a time-lapse photo of a mountain peak. While filming this peak for the majority of the day, it is clear to the camera lens, but there are periods of time in which it is obscured by clouds. Combining all the hours of photos together on average, there will be nothing obstructing the mountain and you will have a clear image of it. During this observation period, the telescopes are pointed at a precise location to capture radio waves at 1.3 millimeters. These are the waves being emitted by Sag A star from deep space, and the telescopes on the Earth's surface are able to collect and record the data. The setup of the telescopes is where the magic happens. Since the EHT is a global network of equipment with bases located in several different countries, there is a lot of space between the telescopes. This is very intentional because the farther the first telescope is from its partner, the longer the baseline the two are allowed to form. With the longer baselines, scientists are able to resolve the small details of images to a higher quality. Because of the precise nature of these instruments, the data taken in different time zones and locations needs to be correctly calibrated. In order to combine the telescope's data and create an image, there have to be very accurate atomic clocks on the telescopes. This means the exact time, location, and position of the waves are recorded in the data. So if there are different angles in the waves once it reaches Earth, it can be accounted for in the post-processing. What the scientists have done is collect thousands of images of Sag-A star, and through a process in which they are classified and averaged, the final result is a clear image of our own Eye of Sauron. Professor Kallstrom explains.
We take the signals, record them in real time, an enormous data rate, and then we bring all that together and correlate it or combine it, analyze it together as if we're observing with one big telescope all at once.
Luciano Rezzolla of the Goethe Institute in Frankfurt, Germany studied and provided a variety of images of Sag-A star. Surprisingly, they show the hole changing rapidly. Its appearance changes significantly in a span of just minutes, compared to the only other black hole we have photographed before, black hole M87 star. The supermassive black hole M87 star is actually consuming matter from its accretion disk at a very active pace, compared to our galaxy's black hole. That said, since it is 1,000 times bigger than Sag-A star, it is also moving at a much slower pace. If our black hole was a person, its appetite would be almost nil compared to that of M87 star, consuming the equivalent of just 1 grain of rice every million years. Because of the difference in its size, M87 star would change visually over the span of days, unlike Sag-A star, which does so in far less time. Chi-Kwon C.K. Chen from Stewart Observatory and the Department of Astronomy and the Data Science Institute at the University of Arizona compared trying to get a clear photo of Sag-A star to that of getting one of a puppy chasing its tail. Scientists have discovered that Sag-A star's photographs are similar to M87 stars but with different and inconsistent shapes due to the vast contrast in size. This is because the gas in the vicinity of the black hole moves nearly as fast as light, and although with a bigger galaxy like M87 star, it could take up to weeks for the material to orbit. With Sag-A star, it can orbit in minutes. Even though they are unable to photograph the black hole itself, they were able to calculate what was happening immediately around it. In its simplest form, the black hole's gravitational pull is so strong that it doesn't even allow light to escape its grasp. This makes them essentially invisible. What scientists are able to capture was the central region known as the shadow, surrounded by a bright ring-like structure. This ring is created by the Schwarzschild radius, which is the distance in which light or material will be pulled into the black hole. We see the radiation around the hole that is a consistent distance away, and the images we capture allow us to gaze into the emptiness of the black hole. These photographs offer great insight into how these supermassive black holes may interact with the surrounding material, as the Sag-A star's mass is 1 million times the mass of our Sun, but all located in one single point. It has a great effect on the surrounding space material. Of note, the similarity in the photos between M87 star and Sag-A star lends credibility to the accuracy of Einstein's theory of general relativity. This news has scientists very optimistic about future finds. For 5 years, scientists employed supercomputers to integrate their data and analyze it. Throughout this process, the Event Horizon Telescope utilizes both theoretical and simulation studies to better understand our own universe. This generated an extraordinary collection of simulated black holes that they are then able to compare with the observations in the field data. These exciting images have been processed and put together from data that was gathered in 2017. But since then, there have been 2 more observation periods performed. According to researcher Leah Medeiros from the Institute for Advanced Study in New Jersey, it could be years before the data taken in 2018 and 2022 is released to the public. What amazing and unique discoveries are you excited for? Tell us down below. And don't forget to like and subscribe to our channel for more videos like this. Until next time, thanks for watching Factnominal.